Welcome back to Inorganic Chemistry. Last time we learned about the basics of molecular orbital theory. In this lecture we'll learn a more complex situation where we have bonding between two different types of atoms, and we'll also learn about orbital potential energies. Heteronuclear diatomic molecules, in particular we're going to look at carbon monoxide. So we're going to go through the same procedure, how to find the molecular orbitals, the bonding in the molecule. So first we need to remember what our geometry is and determine the symmetry. So we know what atomic orbitals are going to overlap. Valence atomic orbitals, that's easy from the periodic table. Okay, so carbon monoxide is a linear molecule. It does not have a perpendicular mirror plane, so it belongs to the point group C infinity V. And so from this character table we know the s orbital will always transform as the most symmetric, sigma plus. So carbon 2p 2s, so we know the 2s is going to transform as sigma plus in the C infinity V point group. We have, again, remember the pz, px, py, and z is the primary rotation axis. So the pz is aligned on that, and that also transforms as sigma plus. The x and the y transform together in this point group as pi. That's on the carbon side. The oxygen side has the same symmetry in this point group. They're along the same rotation axis here. So the oxygen's 2s is sigma plus. The oxygen's pz is sigma, it's going to transform as sigma plus, and the oxygen's 2px and 2py will transform together as pi symmetry representation. So we identified the valence atomic orbitals, we've identified their symmetries, and we could start to overlap them, but we need to take into account their relative energies. We know from electronegativity arguments that the oxygen is more electronegative than carbon, and so it should have lower atomic orbital energy levels relative to the carbon. But how much lower? Well, we could just guess. If we want more accurate molecular orbital energy level diagrams, let's use some numbers. So the numbers I'm going to use, your textbook calls orbital potential energies, and in the past these have been called valence state ionization energies, so I have a table here of that. And these are empirically determined, so using spectroscopy scientists can measure the energies of the electron coming from the atom. So in hydrogen we can measure the ionization energy of the hydrogen atom, and that matches our Bohr model that we calculated. What is the energy of that 1s orbital in the ground state in hydrogen? And we said it was 13.6 electron volts, and we can measure that. Well, that works great for hydrogen, but what about atoms with more than one electron? Well, we learned how to kind of estimate that calculation from Slater's rules, but we want something a little more accurate. So what has been done is measure the ionization energy taking into account possible valence states are more than one for a multi-electron atom. For example, carbon, we know the configuration 2s2 2p2 is the ground state configuration, would have electrons like this according to all of our rules. So when we ionize the carbon atom, we would expect one of these electrons to be lost, and we have equal probability in either of these electrons being lost because they're degenerate. So this is the ground state, but it's very easy for this electron to get excited up to here. So we have a slightly different energy with this electron configuration. We could also have spin pairing in the same orbital, or you could have spin pairing in separate orbitals. So you see that the valence electron configuration of carbon is not just the absolute ground state. It's very easy for these other configuration states, spin states, to exist, slightly different energies, and so each of these will contribute to an average ionization energy for the atom. And so that's what this comes from, we said, well, the 2s electron of carbon has on average 19.4 electron volts when to ionize from there, and the 2p on average has a 10.6 electron volts to ionize from there. Using these empirically determined values can help us determine how strong the orbital overlap will be when we do these linear combinations, because one of our tenets is that similar energy, maximum overlap. Well, how similar? Okay, using these values on this table, we can say that there will be significant atomic orbital overlap when the difference between the orbital potential energies is less than 13 electron volts. So if we go back to our example here, let's assign some energy values here. Remember, we want to end up with an orbital energy level diagram where energy goes up on the y-axis and a free electron would have energy of 0. So how far down is a carbon 2p energy? 10.6 electron volts. Okay, and then the 2s is that 19.4 electron volts. And the oxygen valence orbitals, the 2p is at 15.8 electron volts, and it'd be negative down from the 0. And then oxygen s orbital, valence 2s orbitals at 32.3 electron volts. So now we could draw these on to scale, and we can also see, are they going to overlap? So this 2s on the carbon is not going to have significant overlap with the 2s on the oxygen, because that's much lower in energy due to electronegativity, Slater's rules, or effective nuclear charge, all those considerations. But we will get overlap between this 2s sigma plus and this 2pz on the oxygen. So those are very close in energy, and also with the carbon 2p's. Before we start doing that, there's one more thing we can notice, and that is this pz on the carbon is sigma plus symmetry, and the 2s is sigma plus symmetry on the same atom, and they are less than 9 electron volts apart in energy. So just as we can combine linear combination of atomic orbitals to make molecular orbitals, if they have the same symmetry and similar energy, we can actually combine atomic orbitals on an atom to make a new set of atomic orbitals. And you've done this in organic chemistry. You called this hybridization.